Hello everyone, my name is Mingqi Shao. I'm a student from Beihang University, supervised by Professor Shuo. The topic I'm asked to speak on is a force voltage responsivity stabilization method for piezoelectric touch panels in the Internet of Things. My presentation will include these four parts. First, the background of our research. Second, the innovations of our work. Third, description and performance of the system we built. And the last, the application prospect of our work in practice. With the fast development of electronic and information technologies, the Internet of Things, IoT, is entering into our daily lives. In an IoT architecture, the human-machine interface is a fundamental element, and touch panel is a common type of human-machine interface. Ordinary touch panel can be positioned at the two-dimensional level, but the detection demand of three-dimensional touch force is getting higher and higher. Two-dimensional location touch panel, recessive touch panel has more complicated structures, higher energy consumption, and lower sensitivity than capacitive touch panel. So, capacitive touch panels are more used in smartphones and other products. Self-capacitance and mutual capacitance detection are two methods of capacitance detection. Here, we use self-capacitance detection and use the piezoelectric effect in force detection. But the piezoelectric effect has a problem that the stability of the force response is not high. That is to say, only perpendicular force components can be detected at different touch angles. In order to improve the stability of the force response, we propose the following four innovations: a new touchscreen structure, the angle capacitance model based on machine learning, and finally built a complete three-dimensional touch force detection system to achieve high-precision force detection. Compared with the previous work, we use the real fingers and use the machine learning algorithm and expanded the number of capacitors to 25, and the interpreted force detection accuracy was also improved by 2.5%. Here is a touch panel we made. 25 electrodes are joined on the capacitance detection layer to detect the capacitance change. The force detection layer is a layer of PVDF film, which will generate charge when subject to external force. The layer electrode can lead out the electric charge, and the middle shield layer is used to shield the capacitance and force detection layer to prevent coupling between them. Here is a schematic diagram of the system. There is a gyroscope on the finger to indicate the true touch orientation angle. The touch panel is placed on a triaxial force detector to indicate the real touch force. The information of capacitance detection and the force detection layer is read by the reading circuit to the upper computer. Through the model of the relationship between the distribution of capacitance change and the touch angle, the measured touch angle can be derived from the change in capacitance. Through a simple trigonometric function formula, the perpendicular force detected by force sensing layer is converted into an oblique force, and then compared with the true value measured by the triaxial force detector, the accuracy of force detector of the system can be known. This is a schematic diagram of the reading circuit, which is mainly divided into two parts: capacitance and perpendicular force detection. The core of the capacitance detection circuit is a high-precision capacitance to digital converter, which converts the capacitance change value into a digital quantity and outputs it to the host computer. Where the perpendicular force detection circuit is mainly a charge amplifier, because the force detection layer will generate electric charge and on the upper and lower surface. The charge will be amplified and converted by the charge amplifier to become a voltage quantity, which is converted into a digital quantity via the ADC. In order to establish the relationship between capacitance change and touch angle, we discussed several commonly used machine learning models, and also discussed their performance using different kernel functions. The final results show that the Gaussian regression model with the exponential kernel performs best in terms of angle prediction accuracy, reached 92.7%. And the final overall force accuracy reached 87.5%. The above table is the geometric parameters of the touch panel we built. The following table is some performance of the system, including capacitance, force sensitivity, and force voltage responsivity. In fact, the parameters of each point are somewhat different. The two figures on the right are the capacitance, force sensitivity, and force voltage responsivity of 25 points. It is obvious that there is a difference between them. Our work can be applied in many fields, such as interactive games and writing applications, and can also be applied in the medical field, such as the detection of Parkinson's disease. The studies found that 70% of Parkinson's patients' first symptom is resting tremor, which can be past detecting the condition of finger shake to complete early detection or clinical diagnosis. This has a very broad application prospect. At present, the force accuracy of our system has reached 87.5, which is not very high in practical applications. The direct reason for limiting the force accuracy is angle prediction. So our next job is to find a better capacitance touch orientation angle prediction model. In addition, the volume and power consumption of the reading circuit are also important factors that limit practical applications. Therefore, in the future, we will focus on miniaturizing the reading circuit and reducing power consumption to meet the needs of practical applications. We hope to share our research progress with you here next year. Thank you for watching.